Looks like we both started contributing to GNOME around 2002, so it's been a while. Today we're going to talk about fonts. I'm first going to talk about how we are extending OpenType to be more featureful and powerful, and then Matthias talks about GTK text rendering and advances in the renderers. So what's in this name? The Better Engineered Font Formats is the title of an online presentation I did 3 years ago, and since then we've been working on these ideas, and right now we are pushing many of them through the ISO standardization process. So the advances we want to push are, unlike the previous changes, that we want to make a more engineering effort to change things at a faster pace than OpenType has been previously seen. So there's 3 parts to my presentation. The first part is called boring expansion, better ergonomics, and beyond emulation. So let's start with the boring expansion part. This is where we improve, make incremental improvements to the existing font format. And so far, we want to address decades-long limitations of the format and add desirable features. And the key to the idea is that it's okay if enrollment takes time, because most of the ideas we are pursuing now, we already had them in 2015, but every time we wanted to make changes, other stakeholders would push back because, oh, this will take forever to roll out. And it's fine if it takes 5, 10 years before we can use a new feature. If we had done it in 2015, we could use it now. So with that in mind, there are 4 pieces that we are pushing through the standardization process right now, and I'll go briefly over each and try to make it more understandable for this audience. The first one involves better organization of variable fonts. And variable fonts, if you haven't come across them, are fonts that have more axes, more variations other than just size. So for example, you can choose an arbitrary weight or arbitrary width. And this new technology, the AVAR2 table, allows for building variable fonts in modular ways such that the combined file size can be reduced significantly. That's one of the use cases. One thing about the AVAR2 feature is that after we shipped it experimentally in Esfahbod and FreeType, Apple decided to ship it last year, so they just shipped it without announcing or telling us. So we enabled it by default. It has multiple uses. I'm just going to show one of them. So this is, on the input side, you have the variations that the font can have, a weight, width, optical size, and grade. And normally, when you have 4 axes, you have something like 3 to the 4 corners of this cube that they make. And typically, you have to specify the shape at every corner. That's like 81, what we call masters. Whereas with something like AVAR2, you can convert this design space problem into modular axes that are orthogonal. So instead of having to specify all the corners of the design space, you can only specify the minimum and maximum of each axis. And since they are orthogonal, they just add up and extrapolate correctly. So we can reduce something from 81 masters to 8 masters or 9 masters. So we've seen 80% file size reduction and 70% file size reduction when we applied this technique to a couple of existing fonts. So the other thing we're pursuing is to store cubic Beziers in TrueType fonts. Historically, TrueType fonts have been only quadratic Beziers. By storing cubic, we can save some space and also reduce the conversion error when compiling fonts. It has saved something like 3% to 10% file size as well. We have variable composites. I'll move forward a bit. So historically, in a font, you can build a shape for one glyph out of components that come from the font. but these components are static shapes. With variable components, we can use the same glyph, but at different variation scales. So what this means is that, for example, here, the green shapes are what the font contains, and then by interpolating between them, you can create all the different shapes that are slightly different, but you can't probably see them. So this technique is highly desirable for designing Chinese fonts or Korean fonts or Japanese fonts. For example, for a Chinese font that we tried this, there was a 67 file size saving, and for the Hangul font, a 92%. That means the new font is only 8% of the original font. So the other advance we are making is to allow fonts to contain more than 64,000 glyphs, which is the current limit. Now you might think 65,000 glyphs is more than enough per font, but there's Chinese, Japanese, Korean fonts already go beyond this number. Unicode keeps encoding like tens of thousands of characters there. And there's also pan-Unicode fonts, something like the Noto Sans family currently involves more than 100 different files because they can't all fit into one font. And then you open LibreOffice and you see like Noto Sans Arabic, Noto Sans Devanagari, you see 100 families listed, which is extremely bad user experience. So what we are doing is we are introducing 24-bit glyph IDs, and this allows for up to 16 million glyphs, which should be enough. And in a Noto Sans merge font that we made without the Chinese, Japanese, Korean, we had over 100,000 glyphs just fine. So that was the boring expansion part of the ideas proposal, which we are pursuing in the standardization track of ISO. Now I want to talk about better ergonomics, which by ergonomics here, I'm talking about the developer experience, not the user experience. So what's happening is that currently we have free type for rasterization and Esfahbod for shaping. One is written in a C code base from the 90s, Esfahbod is from the C++ from the 2000s, and we also have something called FontMake, which is a Python ecosystem for font compilation. So what the Google Fonts team are doing is to rewrite everything in Rust in a unified code base such that we can do font access, shaping, rasterization, and compilation all using the same Rust framework. And the motivation mainly is security, but also the compiler will be super fast because Python is just so slow. And then there will be one place we need to implement new features instead of 3. And there's 3 or 4 people working on this actively, so we expect to see it in Chrome very soon and other places, Android and other places later. And then the last part of my presentation is the beyond emulation part, which involves allowing more varied ways to do shaping or drawing from the font. Now, the thing is, if this is all the different shaping models, OpenType encodes just one of the ways you can do it. And this is not a theoretical problem. There exist actually active problems, especially with Arabic typesetting, that you can't express in OpenType. You bump against the limitations, and even if we decided to standardize a solution, as we mentioned, that takes 10 years. But the problem is, the idea is how to go around this and reduce the need of updating OpenType every time we need a new feature. So what I'm proposing is to encode the shaping logic in WebAssembly inside the font, and then interpret it in a secure environment to do shaping instead of being a data-driven solution. So, for example, I mentioned Arabic. There's different Arabic shaping engines other than OpenType because OpenType just cannot do Arabic properly. So Graphite Decotype and other alternative shaping engines exist. So the problem is if you have a font built against graphite or decotype, it won't work on most places. You need a specific shaping engine, and they work together. This doesn't make sense. So a font that works against the shaping engine can, with WebAssembly, just ship the shaping engine itself, and everything will work. This is how it works. You just implement one function and then embed it in the font. So I have a bunch of demos I will quickly go through and then pass it to Matthias. So this is the SIL Graphite demo. So Graphite 2 is an alternative shaping engine other than OpenType layout that the SIL International designed in early 2000s. The problem is it's not shipped everywhere, so it's shipped by Firefox and LibreOffice. So when they build fonts that work against the shaping engine, they only work on certain platforms. Now what I did is I took the libgraphite to code base, compiled it to WebAssembly, and encoded it in the font. The payload is only 90 kilobytes. That's amazing. And with the G-time using, it's 3 times slower than native code, but that's fully acceptable, in my opinion, for custom shaping. So this is an example of what I'm talking about. The left side, you see the dots in the here, they overlap, they collide. That's undesirable. The middle column is what we can do the best effort in OpenType right now. Now, you notice that we space things further just to avoid collisions. The right side, however, is a WebAssembly solution to do proper collision avoidance while keeping everything fit tightly together. Here we have another example of Arabic, a different style. The upper row, the top row, shows the OpenType solution where the left part of every cluster sits on the baseline and everything shifts upwards as you go right. However, it's more desirable that the center of the cluster sits on the baseline and things form around it. And this is almost impossible to do with OpenType currently, whereas with WebAssembly, it's just 10 lines of code. This is an Egyptian hieroglyph. The way they are encoded in Unicode is that there's a push-pop mechanism, so they can recursively contain other hieroglyphs that need to be rendered. Now, the left side is an OpenType solution that only goes 2 levels deep, whereas if you have just code, you can handle the push and pop in a stack and go beyond like arbitrary number of levels. This is, we have someone called Simon Cousins that is amazing at creating demos and new projects. This is, what's happening here is that the shapes are just a stroke, and using the WebAssembly, he's dotting the path and then outputting that as new glyphs. So that's a variable font. You can change the dot spacing and dot sizing. This one is even more interesting. So this is a font that originally was not pixelated, but what Simon has done is he has embedded free-type rasterizer inside the font to rasterize the font and then draw every pixel separately. This one combines color fonts also for anti-aliasing. Now the question is why? Why do this? As I mentioned, even for Arabic, we already have 3 or 4 alternative shaping engines and many other ones that we don't know about, but they are sold in Iran and Pakistan. And for that reason, we don't want to specifically encode one Arabic solution because it's something that's constantly changing and being improved. So another way to look at it is that we want to have pluggable shapers, and people might say this, we don't want this on the web browser, or we don't want this on my system, but shaping doesn't only happen on the web or on the desktop. There's also typesetting, and when you're typesetting something, it's highly desirable that you can just customize your font the same way that you customize your layout engine in Tech or LuaTech. So there's precedent of this move from a static, data-driven representation to fully programmable approaches. For example, on graphics, there's OpenGL shading language and WebGPU shading language. The web itself moved from being static to using JavaScript and WebAssembly. And web serving also started from individual servers, moved to containers, and now there's WASM and edge computing. Finally, typesetting started with Metafont and Tekken, which are programmable. And these days, LuaTech also embeds the Lua engine in the in the typesetter. So you have full programmability at the layout level, but not the font level. So finally, AAT and Graphite chose a state machine way to represent shaping logic. OpenType decided to factor out the script-specific logic and put it in the standard. However, over 15, 20 years, that approach proved to be unscalable as Unicode introduced new scripts. So what OpenType did, added something called the Universal Shaping Engine, which simplifies adding new scripts to OpenType. However, basically, we are going back from this idea that shaping logic should be in the shaper towards a model that the font provides more and more data. At some point, data and code become the same. So instead of encoding the shaping logic in predetermined ways that OpenType understands, we just want to ship the code in there. And the last line, when we applied this approach to one of the Nastaliq fonts that I demoed, the font size shrank by 2/3, so the font is 1/3 of the original. There's also 3 examples that people made out of this technology. So I implemented this WASM shaper in Esfahbod, and the WASM runtime I'm using doesn't have a budget limit, like a time limit of CPU, so it's not a production-ready solution. However, it didn't stop someone to encode a full large language model inside the font with a deduction engine such that you type something and then the font completes it for you. Or another one of them, you type in English and it shows translation in German. So these won't be eventually possible because we limit how much work you can do in the shaper, but it has been already experimented with in these ways. And that was my presentation. This is happening on the Esfahbod/Boring expansion GitHub repo. We have been talking about it at different conferences, and the standardization track is at MPEG. Quick note on Esfahbod, we've seen since I've been here last time, well, not last time, in the past 15 years, we've seen Esfahbod's market share go up in a way that at this point is probably most commonly used shaper in the world thanks to Chrome and Android and other platforms. So this market share gives us a lot of leverage to innovate. However, we're hitting a problem where unlike Microsoft and Apple, who can just ship something and then standardize it later, we have to go through a standardization first before we can ship it in Chrome and other large platforms. So that gives us a few years lag. But otherwise, we're doing very good on the rolling it out. Even Adobe Photoshop, Illustrator, and InDesign now use Esfahbod. And I'd like to thank the Google Fonts team for supporting my work and investing in the open source fonts and text rendering ecosystem. Dave Crosslad is here, actually, if you want to talk to him about Google Fonts. And I recently wrote my thoughts about the state of text rendering in a paper that is linked there. Thank you.
Yeah, sorry for this brief interlude. We were too lazy to get our slides onto one laptop, so we'll fiddle with 2 laptops instead. Does this work? Ah, there we go. It's almost like a live demo. Does it work? One more time. Oh, I'll just maximize it like this. All right. So Behdad talked about complex and interesting things. I'll just show some pictures because it's almost lunchtime. I wanted to start out with this diagram because I'm not sure if everybody knows how the text rendering stack in GNOME actually looks underneath. So GTK is not using half-bus or any of these other things directly. We talk to Pango, and Pango uses font config for enumerating the fonts on your system, and it uses half-bus, what Behdad was talking about, for shaping, and Cairo for rendering. It's not without problems. One of the issues is that whenever a new feature appears in half-bus, where exciting things are happening, as Behdad was just telling us, we always have to figure out how to plumb them through Pango and reach GTK eventually, which can be a hassle. So long term, we kind of want to get Pango out of the way and use half-bus as directly as we can, because that's the focus of development for text rendering. And for now, we are stuck with this situation. So the good news is, in terms of text rendering, nothing happened in Pango basically in the last year, so I guess we could all go to lunch early. But all the action was on the GTK side, actually. If you were at my talk yesterday, you heard me talk about the new renderers that we've introduced and the fact that they are doing anti-aliasing in a better way than we did before. I wanted to, as I said, just show pictures here. So this is a quick illustration of why anti-aliasing is important. On the left here, you can see what a very simple-minded renderer would do when given various shapes to render. We just sample the pixels, and the pixels where the shape happens to, say, cover the center of the pixel, they get colored in, and the others don't, which works okay as long as the shape is larger than the size of the pixel grid. As soon as your shapes become small compared to the pixel grid, you end up just randomly losing pixels. So what instead you want to do is what I try to illustrate here on the right side. You want to do some more sophisticated sampling and ideally color in the pixels depending on the coverage, how much of the shape they cover to get a better result. Yes, the next thing I mentioned yesterday is fractional scaling. Our renderers now do this. We actually get the proper scale from the compositor, and we try to not render too much. I wanted to show some more pictures here that illustrate what fractional scaling is all about. So if the application is rendering to a pixel grid at 1 times, it's just a regular grid. And traditionally, what we've done for high DPI rendering is to just switch to a 200% scale. So we still tell the application about the same grid, but underneath we use 4 device pixels for each application pixel. And that is easy and works well because the device pixel grid and the application pixel grid remain aligned, so there's no complex problems. With fractional scaling, that gets a lot more complicated. Now we get, on my laptop, I usually use 125% as the scale, so you have 5 device pixels for 4 application pixels. And as you can see now, the grids are no longer perfectly aligned, and the application will still render its application pixels, and then GTK has to figure out how to fill in the device pixels, because the only thing at the end of the day that we can fill in are the device pixels. And coming back to the topic of this talk, text rendering, if we if you actually look how this affects what we do with glyphs, if the application is rendering a B, say, and hinting is involved, then we'll try to position the B on the application grid so that the stem of the B nicely lines up with the pixels. And if we then fill this shape in, we get a nice and clear vertical stem there. That's the idea, and that's how it works at 100% rendering. Things look a little different now that we do fractional scaling. We have these two grids here, and if the application is still aligning the B on the, I changed the colors here. The gray grid is the application pixel, so the B is still aligned to the application pixel grid. But the only pixels we can actually fill in are the device pixels. And as you can see now, the hinting actually works against us because it aligned the B to the application pixels and thereby made it so that we are no longer aligned to device pixels, and our nice and sharp vertical stem is now blurred out, which is not a great result. So what our new renderers instead do is we try not to do font hinting on the application pixel level. Instead, we do that only once we have the fractional scale from the compositor and we know where the device pixels are. And then we do the hinting to the device pixel grid. Maybe you can see that here if I go back. Here it was the B, the top left corner of the B was on a application pixel boundary, and now here we shifted it up so that it's actually aligned to the device pixels. And if we then again render, we get again a nice and sharp vertical stem. And that's what GTK is doing with the new renderers. And I hope it makes your fonts sharper and makes everything look better. And that's all I had to show. As I said, I just wanted to show some pictures and let you all go to lunch, unless there's questions.
I'm sure you know the question, it's the hard one. What do we do to make it nice when we're scrolling in text editor so we don't jump around when we're on fractional scaling? Should we be disabling the hinting during a live scroll and then at the end of the scroll snap back? Do we, I guess I'm looking for ideas too, because I need this for terminal widget as well.
I'm not sure there's a perfect answer to that. I mean, it's a difficult problem. What Christian alludes to is that with our hinting, glyphs are moving around a little bit. And if you're scrolling, what can happen is that the glyphs jump up to the next device pixel position. Sometimes they jump up, sometimes they jump down. And if you scroll and if you're very sensitive to this, like some people are, then you notice that there can be some jitter. That's a general problem with animations and font hinting. And to be honest, I'm not sure that we have a perfect answer to this. We just need to try things out and see if we can make it better. Unless you have any good ideas.
No.
So I have memories of, in the past, there have been talks about a GPU rasterizer for fonts or something. Could you, either one of you give us an update, or like, is that not a thing anymore? Is it stalled? How is it?
So that's something that Behdad did more than a decade ago now, like something called Glyphy, which basically
Glyphy, that's the name.
Glyphy,
yes.
Yeah. So the current, what we do in GTK currently is we have a very traditional approach to rendering glyphs. I mean, we do use the GPU for most things, but we rasterize the glyphs with Cairo still, and then we upload them to a glyph cache and use them from there. And what you ideally would want to do is maybe upload the outlines, like the scalable Bezier curves, and then have a shader that can handle those and rasterize them on the GPU. That would be the cool thing to do, and that's what Glyphy was experimenting with. We did a few years ago, maybe 2 years ago now, try to integrate Glyphy into our renderers. And we do have a working branch somewhere that does that. But we haven't merged that yet because other things were of a higher priority. We will get back to, I mean, maybe I should say it's part of a larger problem. I talked about GSK Pass yesterday. That's kind of the same idea. We have Pass as a GTK API now, but we still use Cairo underneath to rasterize them and then upload a texture. That's the same problem. We also want to eventually render Pass on the GPU.
So the idea is to use GSK Path for font rendering in the future, or?
Sorry?
So the idea is to use GSK Path for font rendering too?
I don't think that's the best fit, to be honest. I mean, glyphs are very specialized paths. They have, we talked about hinting here, and that's one of the specialties that you have that are relevant for glyphs and not so relevant for general paths. And in some regards, glyphs are often well-behaved paths because you don't get arbitrary intersections, and usually things are encoded in a way that makes it easy to render them because they have to work with free type and very simple rasterizers. But in general, paths can be ill-behaved, and then the shaper needs to be very robust to be able to handle those situations. For glyphs, that might be a little easier, so that's why something like Glyphy makes sense to treat as a separate thing. But these two things are both open issues that we'll get back to once the color stuff is all sorted out.
Okay, thanks.
Okay, I think that's all the questions that we had. Let me just check online once. Yeah, that's it. Thank you.
Okay, thank you.